how much energy does it take to heat up or cool down a substance? That's what we're going to learn about in this video. So each substance basically takes a different amount of energy to heat up. For example, water takes a lot of energy to heat up even a few degrees Celsius, but something like aluminum actually takes a lot less energy to heat it up by the same amount. So there's actually a very simple equation that we can use. You'll notice it's on your formula sheet, and it is this equation here. Q equals mc delta T. So let's write that here. Q equals mc delta T. Q is a variable we usually use for heat. And remember, heat is just a transfer of energy. So this is going to be in joules. M is the mass of the object that you're heating up. Obviously, if there's more mass, it's going to take more energy to heat it up. C is not the speed of light. Unfortunately, we don't get to use that in this question. C is what's called the heat capacity of the substance. And this is just a value that tells you how much energy it requires to heat up a substance by 1 degree Celsius. Delta T is the change in temperature, or the difference in temperature. So say we're heating something up by 5 degrees Celsius, delta T would just be 5 degrees Celsius. So this is just the change in temperature. So the only really new thing here is this heat capacity term. And as I said, it's different for each material. So on your formula sheet on the back, it actually has a list of what's called the specific heat capacity for a bunch of substances. So you see, for example, water has a specific heat capacity of 4.18 times 10 to the 3 joules per kilogram degree Celsius. So all this means, it looks complicated, but all this means, first of all, let's write it out in normal units, 4180, right? Joules per kilogram degree Celsius. That's what it would be without the scientific notation. And all this means is that it takes 4,180 joules to heat up 1 kilogram of water by 1 degree Celsius. So it's basically how much energy it takes to heat it up. You'll notice some of them, like aluminum I mentioned before, is only 920 joules per kilogram degree Celsius. So it only takes 920 joules to heat up 1 kilogram of aluminum by 1 degree Celsius. So in the question that you're given, you're going to sort of just look up from this table what the heat capacity is in order to find the answer. Notice here on this whole table of all these metals, ice, ethyl alcohol, the thing that requires the most energy to heat up is water. Pretty interesting. So let's do some math with this. Let's solve a problem. Calculate the amount of energy required to bring 5 kilograms of aluminum from 30 degrees Celsius to 2,500 degrees Celsius. So you're really heating up this aluminum. So we know the equation for this, Q. Let's do it in blue here. Q is our heat that we need to add in order to do this. We know it's going to equal to the mass times the heat capacity times the temperature change. And remember, temperature change, we can think of it as like T2 minus T1, right? Our final temperature minus our initial temperature. So in this equation, mass is going to be 5 kilograms. And we're going to include units because we're going to check to make sure they all cancel out. C for aluminum, if you look at your table, again, we looked at this one already, 920 joules per kilogram degree Celsius. So, oops, zoom in a little more. 920 joules per kilogram degree Celsius times delta T, so the change in temperature. And the change in temperature is 2,500 degrees Celsius minus 30 degrees Celsius. So we're basically bringing this up sort of from room temperature, or really warm room temperature, to a very high temperature. So, I mean, we could just do this calculation like this. 5 times 920 times 2,500 minus 30, which gives us a huge number of, I'm going to change this to, so this is 11,000 kilojoules. Actually, you know what? I'll just write it out. 11,362,000 joules. Actually, do we know it's joules? Let's make sure. Kilograms are going to cancel out with kilograms. The degrees Celsius here is going to cancel out with these degrees Celsius, and we're left with joules. So that's why this heat capacities have a bit of a weird unit where it's joules per kilogram degree Celsius, so that it cancels out. Clearly, we can write this in a better form. 11 million joules is about 11 megajoules if we round to two significant figures, which it seems like makes sense for the question. Okay? And as you can see here, the answer here is 1.1 times 10 to the 7 joules, which is the same thing as 11 megajoules. So try the next question yourself. See if you can figure out the answer. Pause the video here, try it yourself, unpause to see the solution. So if you do this, you're going to get an answer of negative 453,600 joules, or rounded about negative 450 kilojoules worth of energy is released. Now you'll notice when we say released, why is our answer negative? Well, if you think about it, we're cooling. So it starts at 32 degrees Celsius and it goes down to 5 degrees Celsius. So our change in temperature was actually negative 27 degrees Celsius, right? Like this is negative 27 degrees Celsius. So when an object is releasing heat, we say that it's negative. It's basically releasing that heat back into the environment. So the energy it gains, it actually doesn't gain any energy. It loses energy. So this glass lost 450 kilojoules to the environment, which is why the answer is negative. I want you to give a try to question 3 yourself. You'll notice the answer is here. So give it a shot, see if you can come up with that. All right, I'm not going to give you a solution to that one. If you have questions about it, you can ask me in class tomorrow, because I want to go on to the next part, which is changing the state of a substance. So we've talked about heating something up or cooling it down and the energy that takes. The other thing that we can consider is what happens, how much energy does it take to turn ice into water, or water into steam, or melt some aluminum, things like that. So if we go over here to our formula sheet, we have a second set of equations that's going to help us out for this case. Q equals mLF and Q equals mLV. Pretty simple equations, because LF and LV are things we can just look up. So the general equation is Q equals mass times some L. And M we know is mass already, so that's the same as the other equation. And L is just how much energy it takes to change the state of a substance. So if you look at the back of your table again, or the back of your formula sheet, it has these things, the specific latent heats for various substances. And what a latent heat is, it basically tells you how much it takes to change the state of something. So for example, aluminum. Aluminum takes 6.6 times 10 to the power of 5 joules for every kilogram in order to fuse it. And fusion doesn't actually mean fusion as in like a fusion reactor. What it means is to melt it, or unmelt it, solidify it, freeze it. So this is basically the energy it takes to melt things. And you'll notice it actually lists also the melting point of aluminum. So aluminum takes 6.6 times 10 to the 5, so what is that? 660,000 joules for every kilogram in order to melt it. And that happens at 2519 degrees Celsius. Then we have here the specific latent heat of vaporization. And this is the amount of energy it takes to vaporize it, to turn it into a gas. So aluminum, if you heat it up to 10,000 degrees Celsius, it's going to turn into a gas. And that's the amount of energy it takes. Water's down here. So water, we know the melting point is 0. So that's when it turns from a solid to a liquid. And it takes 3.4 times 10 to the 5, so 340,000 joules for every kilogram to melt it. So, and then here is the vaporization, so turning it into a gas. Notice that's a very high number. It takes a lot of energy to turn water into a gas, into water vapor. So this L in the equation can refer to whatever state change is required. So usually we call it LF for fusion, or LV for vaporization. So we can finish this. L is going to be our specific latent heat of vaporization or fusion. So let's skip that. We're going to skip this heating curve. We're going to talk about those tomorrow in class. But let's look at an example problem. So for example, 4 here. Calculate the amount of energy required to melt 5 kilograms of aluminum. So we know we're going to use the equation Q equals ml, and melting, another name for melting, is fusion. So that's our formula. We know it's going to be aluminum, and we know we have 5 kilograms of it. So we know the mass is 5. That's pretty straightforward. Let's go over here to our latent heats of fusion of aluminum. So we know that's 6.6 times 10 to the 5 joules per kilogram. 6.6 times 10 to the 5. Got to remember that. So 5 kilograms times 6.6 times 10 to the 5 joules per kilogram. Notice what happens with those. They cancel out. So we can just multiply. And if we multiply 5 times 6.6 times 10 to the 5, we get a large number. 3 million, oops, I should do this in this color. 3,300,000 joules. Or we can write that as 3.3 megajoules, or million joules. That's a lot of energy to melt 5 kilograms of aluminum, which is not like a huge amount of aluminum, right? It takes a lot of energy to melt stuff. And last, we can do question 5. Actually, you know what? Pause the video here. Try question 5 yourself. Unpause the video when you want to see the solution. So the answer I get here is 680 kilojoules. Notice how in this question, we actually weren't given the mass of water. Luckily, water is super simple, where 1 kilogram of water is equal to 1 liter of water. So we can just directly substitute. 2 kilograms is equal to 2 liters, so there, that's what we do. So again, a pretty large number just to freeze water, right? Now, the wording of the question might be a little bit confusing. How much thermal energy is released when water freezes? So this is actually how much energy is released by the water. What does that mean? Well, remember, what is cooling something down or freezing it other than removing energy? So in order to cool down water or freeze it, you need to remove energy from it or release that energy into the environment, right? Removing that energy will cause it to freeze. So essentially, this is how much energy is released. And usually we would say that this is a negative number, right? Just as we saw in that previous question, whenever you're releasing energy or cooling something down, it's essentially a negative number. So we are going to actually manually put in that negative number to represent that the energy was released from the object. It wasn't added to the object. Question 6, we are going to do in class. If you understand everything up till there for now, you're going to be set for tomorrow.